Let me see. Question: are we supposed to make it through all of the things you wrote in the study guide this week? These are the study questions. I mean, if I don't make it in the class, then you need to kind of find information um, offline. Um, okay. So where do we have our beautiful, remarkable? Yes, it's bigger. So that's what we stopped at yesterday. Um, so learning on data, different approaches exist depending on how well you understand how nice is your data, so to say, whether you have well-defined features or not. So you can use one of the following techniques. So today we will go into a very simple model and use it to kind of going through the fundamentals of the learning process and the evaluation and model evaluation process. So we will be talking about memory-based learning. Again, as a use case. So we begin with, again, the more formal definition uh, of the learning task. So we have our percept systems, perception, uh, which is basically a set of sensors through which we observe our environment. That's one, or let's not use S. X1, X, N. So those are sensors. Um, environment is sampled. So now, sensors can be of different nature, so it doesn't matter. The only thing is what matters is that each sensor somehow defines a characteristic of the phenomenon that we observe. And all together, so they form a feature vector. So we transition from some devices, device level to really data. So X, so the bold X, a feature vector. And again, I won't you to have this intuition always in front of your eyes. So vector is a vector. So in a simple case where you have two features, x1, x2, so you have a vector starting from the origin of the space and going somewhere. So, and this is your sample or data sample. So, and the learning task, in the learning task, and specifically today we will be talking about classification task, you have samples in this phenomena that you observe. You have samples of different categories. So again, so this is vector x. So x, x1, x2. And then you have, as I said, in this scenario, so you have different categories. You have somehow samples that belong to category 1, and samples, let's know them as that belongs to category 2 or classes. So, and you always, in these settings, again, so we talk about supervised learning, and compared to unsupervised learning, you always have a so-called ground truth. So what does it mean? You always have a reference base somewhere in the memory. So if you think about agentic stuff, so you have a reference base where you have kind of descriptors of your phenomena, so through feature vectors with given labels. But again, in machine learning task, it's just a data set where you have so the revised learning classification task. So you have a reference base. So data set. So where you have your feature vectors, F1 or X, we use X, X1, X2, and the label. And here you have some incarnations, instantiations of it. So 4, 2.5, 2, 3.5, 1, 1. And again, in this very idealistic and simple scenario, we just by some epiphany assumed that this category, according to these features, are very separable. So, and very is not a proper mathematical term. They're linearly separable, so that you can draw lines between different categories and or invisible border between categories and decide which class belongs to which. So basically, in the model-based case. So you want to build such a model that helps you to determine. But to begin with, we talk about memory-based learning, meaning that so we take our reference base and given a new point, so new p new. You want to decide whether it belongs to category 2 or to category 1. And to do that, it is as simple as to compute a distance in this many-dimensional feature space. So now again, so maybe I'm saying very obvious things, so you help me to complete this knowledge. So yeah, I forgot to write labels like, for example, cat, dog, and maybe that's it, plane or whatever, if it is images that we have here. So distances. What options do we have here? Again, so we let me see. We have a single point. So we have x1 or x and y now as features, x, y. So these are our features. And specific values. So x1, y1, oops, versus x2, y2. Oops. So these are our two samples. So first choice we have is what? L1. What is L1? Manhattan distance, absolutely. Manhattan distance. So which is defined as sum over all features. Absolute value of feature, so feature I along x minus feature I along y. So the second choice, so again in a fast forward manner, so we have our L2, which is Euclidean. Euclidean distance, and it is defined as so these are coordinates, our coordinates. So it's the sum of a square root of square of differences. So our feature y, so minus feature square. So for again for all features, yeah, for all the features. And you can actually continue adding the complexity into the calculation of the distance. So in general form, you have the following equation. It's the sum of absolute value. So feature y minus feature y. I think you should protest sometime if you don't if you see some inconsistencies. And there is an inconsistency here. E 1 over p. So the inconsistency here is in this notation over here. Sorry for that. So here we have feature feature 1, and this is feature 2. And so here we have our x and the x sample and y sample. So then it makes sense. So here we have feature 1 of x, and this is feature 2 of y. Oh, sorry, feature 1 of y. And this is feature 2 of x and feature 2 of y. So basically, the difference between between corresponding coordinates is Minkowski distance. The sum of squares and square root is Euclidean distance, and Minkowski distance is a general form. So for higher p. But then the question is, which metric is to use when? Yes. Hmm? What are you going through right now? So how to calculate distances? Very basic geometry between two vectors. Two features. Two vectors. 2 points in two-dimensional space. So you have two-dimensional space. You have two coordinates, coordinate 1, coordinate 2, and you want to compute the distance between 2 points. And then so this is a general form where you have more than 2 coordinates. So you have I coordinates or n coordinates. So I is a iteration, and then so you compute Manhattan Euclidean or Minkowski distance. So, but again, the question. So that was obviously simple. The question is which distances to use when. So can you reflect on this, or maybe call to your memories from previous studies? Yeah, with respect to magnitude of the component vector components. So if we have first case, so if we just compare L1 and the distance compared for distance computing using L2 metric. So first we have a distance between 2 samples. Two feature vectors. So distance computed with L1 and distance computed with L2. And higher n or so towards Minkowski distance. So think about the difference between magnitudes of coordinates. So that in one coordinate, the difference is bigger than in others. So here, for example, if you have many medium discrepancies, so the values in features are quite balanced. So in general, so distance computed by using Euclidean distance will be higher for medium discrepancies. In individual features. So the metric become more sensitive to individual magnitudes. So the higher order of the distance you of the norm you use. So for Minkowski distance, or for high P, so a case with all coordinates being equal and a single coordinate with a high discrepancy. So the distance, the Minkowski distance will prefer this sample. So one outstanding feature will be preferred by Minkowski distance.
Smaller or bigger?
Huh?
Like what do you mean by preferred?
So if you so if you have so basically your decision will be modulated by this single feature. So if you use a high order norm. So it's rather than looking at average discrepancies along all the coordinates. So it will be more selective to this particular feature with large difference in values. So in addition to for example, in lab 1, so you will use you will test whether it makes any difference when using Manhattan distance or Euclidean distance. In addition to this, in many cases, you can implement memory-based reasoning using so-called similarity measure. So that is a distance, and an alternative to it is a similarity measure. So in similarity measure, so you focus on the angle between the vectors. So if you have samples or data points, so like D1, D2, versus D3. So what you want to do, you want to measure the angle between the vectors over here, and this you do using a measure which is called cosine similarity. So cosine similarity is defined as uh, sum of pairwise products of coordinates. So again, if we have our features, feature 1, feature 2. So in two-dimensional case, it is so feature so so this is feature 1 of D1, and this is feature 2 of D2. So you basically take so feature 1 of D1 multiplied by feature 2, feature 1 of D2, and add feature 1 of D feature 2 of D1 multiplied by feature 2 of D2. And you divide by product of norms for feature vector of D1 and feature vector of D2. So this the nominator part is a dot product. So sometimes for assessment of similarity, people use dot product. So just to avoid computation of norms. And the only thing is that dot product is not bounded. So cosine similarity, when you divide by norm, so it will be bounded between 0 and 1. So the closer cosine to what? So for smaller, for a case where angle 1 is smaller than angle 2, so alpha 1, alpha 2. So you say that D1 is more similar to D2 rather than the D3. So let's see. So now we are able to compute distances or a similarity measure. So they reflect different aspects of proximity, so to say, but used interchangeably in many times. So now we want to assess the performance of our model. So how to do that? So assessing. Of a classifier. So as a simple case to start with, we consider a binary classification task. In binary classification, so we have two categories. So class 1 and class 2. And we will talk about it, continue talking about it tomorrow when talking about support vector machines. But historically, so one of the classes, so since it's a binary case, historically, one of the classes is called a positive class. So P, or a negative class. So that will be our N. And the outcome of our classification can be a desired one. So where you classify positives as positives, so class 1 as class 1, or negatives as negatives. So samples that belong to class 2, they are classified as class 2. So correctly classified samples. So true positives, so which is TP, and true negatives as true negatives. And then obviously we have two other cases where our model makes an error. In this case, it's either positive class classified as negative or negative as positive. So in one case, we call it so false positives. So which is negatives classified as positive, and false negatives. So where positive samples classified as negatives. And so we have four choices here, and we can summarize them in the table. So basically, we have our positive samples. So here we in the column or in the rows, we will write outcomes of our classification. So so positives, or class 1, or negatives, class 2. And in the columns we will record the checking with the correspondence of the true values of the desired outcome. So this is de facto outcome and the desired outcome. So here and here. So we have here, we have true positive. So here we have positives. And here we have negatives. True negatives, false positives, and false negatives. Okay. So we will assess our classifier by checking the statistics of correct classifications and false classifications or errors. So that's what we will call based on this table, we will we'll compute performance measures. So which are accuracy, so please help me out here. So accuracy is what? So it's true positive plus true negatives. So total number of correctly classified examples divided by all possible outcomes. So true positives plus false negatives plus false positives plus false negatives. Oh, no, sorry. What?
True negative.
True negatives, yes. So then other metrics we can define as precision. So it will be true. So you take true positive, so all correctly classified examples. So the diffraction of correctly classified examples to fraction of all examples classified as positives. So you take true positive plus false positive. So you for precision you look at these values, and this matrix is as you can imagine is called confusion matrix for a classifier. So how it confuses with different classes with what. So precision. So you take true positive and define and divide by the sum of true positive and false negative. So, and this is called precision. Recall. Recall. So you have true positives divided by true positives plus false negatives. Right. And there is another averaging metric, which is called F1 score, which is defined as 2 multiplied by recall multiplied by precision and divided by recall plus precision. Right. So these are basic definitions of the performance metrics you can use, but they are defined for binary classification. So how can we go around the multi-class case? In multi-class case, so the difference in multi-class case, so when you have more than one category, so you have a large confusion table. So classification 1, class 1, class 2, class N. So these are your outcomes, and the desired outcomes are here: class 1, class 2, class n. So now for a given sample, so you take so now you want to characterize accuracy. So a given sample could be again somewhere here. So we look at the statistics of class n versus class n. So in this confusion matrix, so false negatives is a sum along the row without the element itself. So if you take, so let me take another element. So here in the middle we have class I somewhere, and here class I. So false negative is defined as sum along row I without the ith element. And false positives then is sum similarly is a sum across the column, corresponding column. False positive is sum along column I. Without I element. So as simple as that. So all this performance metrics are implemented normally in the frameworks, so you don't need to kind of compute it by hand. So confusion matrix is also constructed for you automatically in a given classification task. But it's important to understand the principles of its construction. So let's take a break, and we will talk after the break about how to work with data, some very important aspects. So how to correctly approach to experimentation with data and evaluation of classifiers.
Это тот OneDrive, который я хотел добавить. Просто хочу PowerPoint лекции, чтобы свои подсказки себе сделать.
Давай после этой лекции проверим, что там. Okay, so let's continue. So let me resume sharing. So I want to draw your attention to this paper over here, because, well, today I will open up the description of the project, of the mini project that you will do. And so you can read this paper, and it is about evaluating lots of classifiers on many data sets. So, and that will be the base for your mini project. So you will use these data sets and train your own models and verify. Hopefully, you will verify the findings in this paper. So that this paper apparently is became one of the benchmarks for training models, but it also exhibits some important caveats when working with data sets, which I want to talk about today. So well, let me see. Mm-hmm. And yes. So experimenting with data, training classifiers. So just a little bit about the use case with this from this paper. So they use a repository, a data repository called UCI dataset. So which contains 121 data sets. And normally, when you when you want to publish, for example, a new algorithm for classification, you want to evaluate on a large set of data sets. And as I said, so that is one of the typical benchmarks. Although some people say that, I mean, it's not really large data set, so the number of samples in each could be rather small. But that's not the point. So here you have a task. So evaluate your models on many data on different data sets, and here is the repository. And it is here when it becomes rather tricky and or to how to systematically work with data. So just for your understanding, so out of this 121 data sets, 19 of them are so-called separated. So you are given data with clearly or beforehand defined training and testing parts. So 19 so-called separated data sets. Which have separate train and test parts. 102 of these data sets are what we will call non-separated. So that happens. Why not? I mean, you just have a data. You have to decide what to do with it yourself. And then again, so despite this long history of experimentation with machine learning algorithms, so there are still very different approaches to report results. So here I want to give you some main rules, so to say, on how to work with this. So here we have a single data set. So we come to first point to ask again. So maybe you already tried training your own models. So what is, say, a conventional way of evaluating performance of a classifier, like systematic evaluation of performance of a classifier? So given a chunk of data.
Depends on the data.
Can you elaborate? It really depends.
It's evenly distributed among classes, and accuracy is.
You are talking about sensitivity of metrics to different to different cases. So if you have, that's true. So that's why we have this F1 score, for example, metric. So for example, accuracy is not always super informative, or is not only informative metric for evaluating your classifier. So that's what you mentioned. Thank you for that. So your data can be unbalanced with respect to number of samples belonging to one category versus another. So if this is the case, then accuracy could be a wrong or less informative performance evaluation metric. So that's true. So and in this case, you would rather go for F1 score evaluation. So, and yes, that's totally correct. I mean, the super important moment, you need to understand your data. So you before just jumping on and trying to do something with it. So you look at the data and trying to understand. So here I want to put it in the in the context of working with specific data sets. So you open up a folder, and then you either see two files, one for train, one for test, and another one in another folder you have a single file, which we call non-separated. But now you want to you have an algorithm, so you want to train a model that's do classification for this data set. And this model normally exposes several tunable parameters. So there are not that many. Well, actually, there are no tunable parameters in the memory-based model. So KNN. No, it is. It is K. So in the memory-based model, so what we talked about before, there is a single tunable parameter which affects the performance. So if you permit me, if we go back here to this case, so the memory-based model. So why did we talk about distance evaluation? So you keep the samples of your data in the memory, like everything, and then that is your model, basically. So the whole memory, and then you take samples from your test set and try to see to which category it belongs to by computing a distance. So the smallest distance is the smaller distance to a given sample in the memory. So you assign, you decide that this particular test sample belongs to this category. And then, that's what I described when you just pick the closest sample from your reference base. It is called nearest neighbor model. But then you can think that this nearest neighbor model can be kind of very restrictive, so to say. So if your sample is located somewhere here, so then so it may be closer to a wrong sample, while the majority of other samples in the vicinity belongs to a different category. So an obvious extension of this memory base is to look at the K neighbors. So K neighbors, and decide by majority, so to which which label to assign. And this is the first case we see a parameter which.
When do we use that validation set?
We will come to this. Yes, we'll come to this right away. So because before going into validation set, so it's important to understand that each model, even this simplest one, so its performance depends on number of tunable parameters, and these parameters are called hyperparameters. So those parameters that you tune to improve the performance of your classifier according to the metrics that we discussed. So in the KNN method, it is K, the number of methods that you take into account. However, again, so choosing, so here the intuition is simple. So small case, you become more specific. Large case, so then you have a large variance. So in your model, so for a given data, you need to find this sweet spot for this parameter K that delivers best classification. And now we come to the interesting fact. So how to choose a parameter. And again, so immediately you can reflect that the number of tunable parameters can be very large, very large. So, and the systematic approach to choose hyperparameters is to use validation data. So while training, of choosing or tuning hyperparameters. Use validation data. What is the difference? So here I already mentioned we have a training data, we have test data. So when we talked about just data sets that are given to you. So obviously, again, self-explanatory. So this data we will use for testing. But what is validation?
From the other courses, validation data is what we use
to tune
your
hyperparameters. Yes.
Test data is just
Exactly. So sometimes you can even have a validation set kind of as a separate data supplied to you. But in many cases, or commonly, you either have a single data set or two data sets. So what are the options there? So we talk about data splitting approaches. Splits. So maybe the most standard way of doing, well, not the most, but the most straightforward way of doing is you take your train data and you split it into two parts. Normally, you do it by practically you need to first shuffle the samples randomly, and then you do splits. How to split it? So again, so there are different approaches. You can start with say 50-50 splits. So that's totally valid. The important thing is to specify. So whoever you give your model and say, here is my model. It works fine. You must specify how you test it so that other people can reproduce it. From this standpoint, you really have free hands to choose the splits, but you need to make it to do it systematically. For example, if you have a single train data, so normally you do 80-20 split for training and testing. So that's a kind of magic number, 80-20. Here we have a case where you have already two splits, so train and test data. And in turn, now you want to split train data into train and validation sets. So in the most straightforward way, you do it like 50-50. So 50-50. So in a general case, we will be talking about cross-fault validation, which is this. This strategy is applicable when your data is rather small. So and small again, maybe hundreds. So in all machine learning models, you need lots of data for training. If your train chunk is sufficiently large, so maybe you don't need to you don't need to do cross-fault validation, and you can be happy with this static split into 50%, 50-50 on train and validation. And so the idea here is that so now you have several hyperparameters. So you here on this set you train your model. So for a different choice of hyperparameters. Settings of hyperparameters. And for each setting, you test the performance on the validation set. So test for each configuration. So what do I mean here? So if you have k nearest neighbor, so single parameter, but it can be 1, 2, 5, 10, whatever. So you train them all on the training part, so one at a time. So and use the validation part to compute the performance metrics as we discussed, so confusion metrics and all this metrics, and select the best performance, the best configuration for which you were kind of happy with the outcome. After that, you take this best configuration and apply it on test data. What does it mean? It means that you take the test data and you start training classifier again on the entire on the entire test data. Sorry. You should stop me when I say such things. Indeed. So here you split the train data into train and validation. You select best configuration. For testing, what you do, you take the entire train set. So now no splitting, entire train set, and train your model with the best configuration on the entire train set, and verify on the test data, which you never seen before. And that's crucial thing. So train on entire train set for best configuration with best configuration. Best. And test on test data. So now, again, so in many cases, yes. So let's take it again. You're about to train different machine learning algorithms and verify accuracy, for example, of algorithm A versus algorithm B, because you want to choose which one. Each algorithm has a number of tunable parameters which affect the performance. in the simplest case where you have nearest neighbor memory-based model, so you have a single parameter, k. So the number of neighbors to take into account to decide to which class it belongs. So you need to choose this k such that it behaves on average good. I mean, so that you can be totally sure that your model, in most of the cases, delivers good results. And the way to choose it is that first, it's important to separate train and test data. And that is important from the point of view of testing so-called generalization. So you really, ideally, you want to be to have test samples which is never seen during training. So, but so here you do additional split just to have something for intermediate testing. So this validation set. Once you once you are happy with specific configuration of parameters, so hyperparameters, you say, okay, so now I want to do the final testing. To do the final testing, you take this configuration. Now you join all these two sets and train the model and test on the test set. In the case of small size of the training data, so there is a technique which is called cross-fault validation. So when data is small, so the number of samples is small. So this is your data. So a single chunk. So all the samples. So sample 1. Sample, say 10,000. So that's the only thing you have, along with the obviously label. So labels. So the categories for each sample. So what you do, if you have this single chunk of data and you want to, for example, splitting it in half will result in a very limited number of samples, not enough to train the model. Then there is a technique which is called cross-fault validation. So you split your data into chunks. So you will use the entire data set both for training and validation, but iteratively. So you split it into, say, 4 chunks or 3 chunks for simplicity. So and you call it fold. So you kind of fold your data set. So fold 1, fold 2, fold 3, and then you use first 2 folds for training, fold 3 for validation. But then again, you need to do several iterations of training. Then on the next iteration, so you use fold 2 and 3 for training, fold 1 for validation. And in this case, you statistically you collect statistically significant performance. Yes. But splitting data is one thing, which is important thing. Another important thing is pre-processing. So you need to be sure that your feature, the values of your features, are somewhat homogeneous, so that none of them exhibit very large deviation. Because as I mentioned before, some metrics, some distance metrics can be sensitive to this large deviation. So you want to standardize your features. And in Canvas, you will see, so there is a tutorial on typical standardization. So you do Z transformation, you do normalization and whitening. So basically homogenizing the values to have, for example, unit variance, zero mean, which is important, and in norm, the norm of a vector being 1. So all this you need to do before starting your training. But then again, so the important thing is how you do pre-processing. So the standard approach and most commonly used is that you do pre-processing on the trained data. You choose you configure parameters of data transformation. I mean, for pre-processing on the training data. What do I mean? Again, so the pre-processing transformation, for example, is make data zero mean. So you need to compute mean value for each feature and subtract it from all samples. So in this case, your values will be shifted and centered around 0, right? But that's the procedures you will read in this document, which is linked in Canvas. The question is on which data you configure the parameters of this transformation. So because as we have seen here, so there are quite some splits. So you have different data. So you it's not an obvious question how to do that. So what happens if, for example, you use all data to compute zero min? So what is the effect of it? Like everything. So you have test data, you have trained data, and you want to compute zero mean and transform your data to be. So what happens in this case? You implicitly use the information from the test set to configure transformation of the training set. So this is called data leakage. So normally, commonly, so you should compute parameters of your pre-processing transformations on the trainings on two sets separately. So and use one set of parameters for training and another set of parameters for testing. However, here is one practical problem. And some data sets in this 121 series are of this kind. So this common approach works when you have kind of homogeneous distribution of samples in the train and the test set. In some cases, for example, training set and training and testing sets are unbalanced. So, for example, with more positive or with samples with, for example, more positive features on one side, or maybe mixed values on one side, and samples with only positive features on in the test side. If you do normalization, if you do selection of parameters for transformation separately, then most likely the accuracy figures will be low. So, but we are coming back to this simple statement. You need to understand the data. It's not that you're and in AI machine learning you work blindly. So you must understand the data in order to correctly interpret the performance parameters. So let me just reflect this. So common approach. Do configuration of data preprocessing. Separately. For train and test set to avoid data leakage. So however, in the again, you have to be aware that in cases with different distributions, data distributions within training and data sets, this approach may lead to bad performance metrics that you compute. Right. What else? Yeah. Next. So we talked about data splitting and for choosing configuration of configurable parameters. There is a large class of models, especially neural network-based models, where the algorithm itself is initialized randomly. So, for example, in artificial neural networks, weight matrices are initialized randomly, so from certain distribution. And depending on initialization, so you can get rather different results with respect to convergence and accuracies. So in algorithms which rely on random initializations, you need to perform several experiments and average the results. And this is okay, let me see. In the algorithms, with a random initialization. For example, artificial neural networks. Repeat all experiments with multiple seeds. Seed values. So basically, for each seed, you compute, you do all this trouble of doing, cross-fault validation to choose the correct values of parameters, and then you repeat it for different seeds and verify that yes, that is the correct configuration that leads to good performance, and then you finally test it on your test set. So all in all, working with data is a very, very time-consuming process. So, and in many cases, you need to maybe when working for a mini project, you need to spend more time on writing automated scripts. So doing all the iterations for you. Let me see. I have just question. Why different seed values? Can we just use same? No, but as I said, so random initializations can result in different behaviors of the model. So not all models have randomness in them, but whenever you have randomness, then you may expect very different behaviors. So and you need to choose basically configuration which work on average good. But it's a correct question. So practically, it also depends on you. So if you want to deploy your model, so you test it for different initialization, and then you use maybe the best seed in the production model. Yes. Okay, that's it for today. So data splits, model evaluation. So think about writing automated scripts to perform systematic choice of hyperparameters. Tomorrow we continue with support vector machines. See you tomorrow in Zoom.